Hello and welcome. My name is Keith Barker, and in this video you and I get to take a look at the spine leaf architecture to identify, first of all, what is it, why do we need it or want it, and then third, to take a look at it in action. And a spine leaf architecture is very typical inside of a data center. So let's go ahead and draw some racks of gear at a typical data center. So let's label these as rack number 3 and rack number 4 and rack number 5 and rack number 6. And let's imagine that inside those racks, they've got some amazing hosts. Let's go ahead and put 4 of them in each of these racks. And then we'll go ahead and label those as host 1 for the individual hosts that are in this rack of gear, and host 2, and host 3, and host 4, and the same for the other 3 racks here in our little mock data center. And let's also imagine that each of these servers, these hosts, are supporting multiple virtual machines, maybe a dozen or more virtual machines on each host. So let's imagine that VM 11 is running on host number 1, and another VM, let's call it VM 12, is running on host number 2 inside of this one physical rack, rack number 3. Now, if these two VMs were running inside the same host, they could have logical virtualized networking to allow them to connect to each other. But if this VM 11 is on host 1 and this VM is on host number 2, we need to have some networking between them. So on each of the racks, we could add 1 or more switches that allows that connectivity. And so I'll add one of those switches to the top of each of these 4 racks. And let me call this one switch 3. I'll call this one switch 4. And this one switch 5. And this one switch 6. And then each of these physical servers would have connectivity up to that switch. Very likely more than just one for some fault tolerance and some additional throughput. So I'll put some cables there. It's also very likely we'd have a couple of these switches at the top. And that way, if a single switch failed, we wouldn't have a single point of failure. So let me draw the rest of the connectivity in here. Let's also imagine here over in rack 6 that we have VM 33 that's running on host 3 and VM 34 that's running on host 4. And very similar to what was happening over here in rack 3, here on rack 6, if VM 33 needs to communicate with this VM 34 because they're on different hosts, it would use the networking provided between those two hosts to facilitate that. And we're also going to have some virtualized networking on each of the hosts. So here on host 3, if VM 33 and let's say VM 23 were on the same exact host, those two VMs using logical networking in that host could communicate with each other. But anytime we have to go between two physical servers, we're going to need some networking that provides connectivity between those servers. So are you ready for our next challenge? Here it is. What if this VM, VM 11, which is currently being hosted by host number 1 here on rack 3, what if it needs to communicate with VM 33 over here, which is running on host 3 on rack 6? Once again, we're going to need some physical connectivity. In this example, we need some connectivity, networking connectivity, from the servers and the hosts here in rack 3 to the hosts over here in rack 6. So let's add some switches that can allow that connectivity. I'll just go ahead and put a couple in here. And let's call this switch 1 and switch 2. And when I'm using the term switch here, I also want to imply multi-layer switching. There are devices that can do layer 3 forwarding based on IP addresses and layer 2 forwarding based on MAC addresses, depending on how they've been deployed. So for the connectivity from switch 3 to these higher layer switches, let's go ahead and I'm going to use a red color, and let's represent that red is connections that are using layer 3. So there'd be an IP network associated with this segment between switch 3 and switch 1. And for fault tolerance, we'd want to go from switch 3 to this guy 2, and there'd be yet another layer 3 subnet. And then from switch 4 to switch 1, and switch 4 to switch 2, and then 5 to 1, and 5 to 2, and then 6, I'll go over the top here, 6 to 1, and 6 to 2. And for these networks, we could use a /30 or a /31. Sometimes that's allowed. So it's not going to tie up a big block of IP addressing, but I wanted to represent that the connectivity between these upper level switches and these top of rack switches, that's going to be layer 3 connectivity. So here's the great news. If host 1 needs to forward traffic on behalf of its VM 11 over to VM 33, that traffic from host 1 would go through this top of rack switch, and then it has 2 paths. It could go through switch 1 as a routing decision, and then with switch 1's connectivity over to rack 6, that traffic could be forwarded down to host number 3. So that'd be one path. I'll go ahead and draw that here. There'd be one path. And another path would be going through switch 2, and that would look like this. So as a result of this design, here are some of the benefits. We have 2 equal cost paths to get from this rack here, rack number 3, over to rack number 6. So we have equal cost paths. We could use multi-pathing. Also, we have some fault tolerance. If we lose one of these switches at the top here, switch 1 or switch 2, the other one still is providing connectivity, and we still have communications between these 2 racks. So let me go ahead and remove that path for a moment. And let's talk about some interesting names they have for these switches. For these switches that are placed at the top of the rack, and that's just for convenience, they don't have to be at the very top of the rack, but they're often referred to as TOR, or top of rack switches. Also, this layer right here, these top of rack switches, are also making up what's known as the leaf layer. So if you take a look at the spine and leaf architecture or spine and leaf design, these top of rack switches are literally the leaf portion of our spine leaf design. And for these switches up here, I'll go ahead and put a little dividing line. For these switches up here, these are considered to be the spine switches that are providing connectivity between the top of rack switches. So when somebody talks about a spine leaf design or a spine leaf architecture, they're talking about exactly this. And if we were to add another rack, let's go ahead and add another rack. We'll call this rack number 7. This new rack would also have a top of rack switch. We'll call it switch number 7. And it would have connectivity up to the spine switches. So in our case, I just have 2 spine switches here. But if we had 10 spine switches, we would have 10 connections from this top of rack switch, one for the connection to each of our spines. Another thing to note is that the spine switches themselves, they don't have cross connects between them going horizontally. Also, the top of rack switches also do not have connectivity between them. However, each spine switch has a connection to each and every leaf switch, and every leaf switch has a connection to each and every spine switch. And what this facilitates is connectivity between the hosts in any of these racks and the host in any other racks on behalf of the VMs that may need to communicate with each other. So VM11 here can communicate with VM33. Maybe this guy's on the 10.3 subnet, and over here, this VM is on the 10.6 subnet, and they have a layer 3 routed path they can use to reach each other. However, what if we wanted to put VM11 here, which is over here in rack 3, and VM33 over here in rack 6? What if we wanted to logically place them in the same layer 2 network, the same broadcast domain, the same VLAN? Well, one of our challenges, we don't have trunks up here that are connecting all the switches together, but rather what we have is layer 3 connectivity. So how do you extend a VLAN over a network if you have routers in the way that are doing layer 3 forwarding? And the answer is using VXLANs. And that's what I'd like to talk with you about right now, that can leverage this kind of architecture with a spine leaf design and allow devices over here in one rack of gear to be in the same logical VLAN as a VM that's in a completely separate rack, even though they are not directly connected at layer 2. So this represents the leaf layer of our switches, our top of rack switches, and this represents our spine layer right here. And thus we have full connectivity between each spine device and all of the leafs, and each leaf has full connectivity to all the spine switches. So we can imagine that each of these leaf switches represents a separate rack. And I've also placed some devices on our topology that we can play with and look at the results. And as a reminder, all the connectivity between the spine and the leaf, it is all layer 3. So there's no native extensions of a VLAN, for example, from over here in rack 3 over here to rack 6. But what we are going to do instead is we are going to use VXLAN. And that's an acronym for Virtual Extensible Local Area Network. So they took the second character there for the X to make the acronym VXLAN. Effectively, we can choose to put devices even in separate physical racks, even though they're not connected directly at layer 2. We can logically place them in the same VLANs by using this concept called VXLAN. And here's how we're going to pull it off. For these VXLANs, we're going to create some identifiers for the VXLANs. These are commonly referred to as VNIs. I've also seen them as VNIDs. So let's imagine we want to create an identifier of 6783, which happens to be my CCIE number. And let's imagine that we want these two devices here on this left-hand side of our network. We want them to be a part of that VXLAN of 6783. And we want these two devices over here on the right-hand side of our topology also to be in that same VXLAN of 6783. So as far as the actual subnet address that we're going to use with that, let's use 10.9.0.0 with a 24-bit mask. And let's imagine that PC6 is at .6, and the server here is at 106. And over here on the left-hand side, this guy is at .3, and the server is at .103. All of it in the 10.9.0 address base. Now, at first glance, you might think, well, how in the world is that going to work? I've got these devices on the 10.9.0 network over here. I've got these other devices on the 10.9.0 network over here. How do I get the traffic across these racks in the same VLAN? And the secret and the answer to that question is by doing tunneling. we're going to set up tunnels. Now, these tunnels can be manually set up and statically configured. Also, they can be dynamically discovered. There's lots of different ways of doing that. But at the end of the day, we're going to set up tunneling between our leaf devices. So I'm going to put my tunnel in this color right here. I'm going to put a tunnel in from leaf 3 over to leaf 6. And I'll kind of fill it in here. And one interesting thing about a tunnel is that it has 2 endpoints. We're going to have one endpoint over here on leaf 3 and another endpoint over here at leaf 6. And these endpoints are referred to with VXLAN as VTEP, which is a VLAN tunnel endpoint. So with an IPsec tunnel, we're taking the original payload, encrypting it, and then we're putting it inside of a whole brand new packet, and then it's shipped across the network to the other peer who then decrypts it. And a very similar concept works like that with VXLAN, except instead of encapsulating for the benefit of encryption, we're encapsulating for the benefit of forwarding traffic to make these devices in this VXLAN believe they are on the same subnet. And it's accomplished by taking the original payload from layer 2 up, and then re-encapsulating that inside of a packet which we're going to forward over the tunnel. And I think a fantastic example would be this. Let's imagine that this PC right here does a ping to the address over here on .3, which is 10.9.0.3. So that initial ARP request is a broadcast. So originally, the broadcast is an ARP request, and the source MAC address would be PC6 MAC address, and the destination would be the broadcast address at layer 2. And here's what leaf 6 will do. It'll take that original request like this, including the layer 2 header, and it's going to re-encapsulate it into a whole new datagram that looks like this. So this is our payload. It's going to have a VXLAN header that's going to identify the VXLAN it belongs to, 6783 in this case. And then at layer 4, it's going to be using UDP. And then at layer 3, it's going to have the source address of switch 6, whatever the VTEP is for switch 6. And for the destination IP address, it's going to be the VTEP, or the logical end of the tunnel that switch 3 is supporting. So the destination is going to be switch 3. And then the layer 2 headers are going to be swapped out as that packet is forwarded across the network. So the actual path of the traffic would be going from this leaf to either switch 2 or switch 1, who would then forward it down to leaf 3, who would then take a look at the header and say, oh my goodness, I see what this is, de-encapsulate it, and then simply forward the original layer 2 frame down to this VLAN down here. At which point PC3 would see it and say, oh, there's a request, an ARP request from PC6. It would respond, and then that traffic would once again be re-encapsulated at leaf 3, shipped logically over the tunnel, where leaf 6 would de-encapsulate that, and then forward the response down to PC6. So the actual literal traffic is being routed over the network. However, the logical path is through the tunnel between the 2 leaf switches. So the benefit of VXLAN in the data center is that we can logically place devices in the same layer 2 broadcast domain, even though those devices may be separated by 1 or more layer 3 routers on the path to get there. Again, it's all done through the tunneling mechanisms that VXLAN uses. So I thought to myself, wow, it'd be really cool if we could take a look at the packets involved when VXLAN is in use. And I just so happen to have a topology. It's the one we're looking at that I'd like to go ahead and demo for you right now. And here's the lay of the land regarding IP addressing for the tunnel endpoints. Here on leaf 3, I'm going to be using 10.10.10.3 as the tunnel endpoint here on leaf 3. And the other end of that tunnel for this demonstration on leaf 6 is going to be 10.10.10.6. So if we looked at the routing table from leaf 6's perspective regarding how to reach the other end of the tunnel, it's going to have 2 paths, one that goes this way, one that goes that way, and as a result of it having multiple paths, it can use equal cost multipathing, which is fantastic. And that way we can send some traffic this way and some traffic that way and get more throughput as we're forwarding traffic over the tunnel on behalf of our host and VMs. So here from the perspective of leaf 6, if we do a show NVE and a question mark, and let's go ahead and take a look at peers. So here it's showing that we have a peer at 10.10.10.3. That's the leaf 3 switch. And if we do a show NVE peers and detail, here it shows us that the peer state is up. It's also specifying that the virtual network identifier that it's supporting is 6783, and that is the same virtual network identifier that we're using. So if we did a show IP route for that specific route of 10.10.10.3, this will help us confirm that we have multiple paths to get there. One going out Ethernet 1/1, the other going out Ethernet 1/2. Also, let's do a show run, and let me share with you a few tidbits from this configuration. So currently I have VLAN 9, that's the local VLAN on this leaf switch, and I've associated with it the VN segment, the virtual network segment of that VXLAN ID of 6783. So the play-by-play is if we have this switch and we have a device connected to, let's say, port 1/7, which we do right here, if we assign that port as an access port in VLAN 9, based on this configuration, that client is also logically going to be in the VXLAN 6783. So if the client sends in a broadcast, like an ARP request, this switch will take that, re-encapsulate it, forward it over to the peer, who will de-encapsulate it, and then forward it down to the other devices that it has locally, which are also associated with the VXLAN of 6783. Also, just to confirm, who do a show interface status. And let me scooch this over just a little bit. Here it's showing us that Ethernet 1 and 2, these interfaces here, are layer 3 connections up to the spine layer. Also port 6 and 7, which I have configured right here. They are configured as access ports in VLAN 9, which, based on our configuration, is also associated with the virtual network ID of 6783. And switch 3 has similar treatment for ports 6 and 7 over here on its side as well. So here's what I'd like to do. Before we send traffic from PC6 or server 6 over here to server 3 or PC3, let's do some captures on E1/1 and 1/2 so we can actually see the VXLAN traffic and the re-encapsulation that's done as part of the tunneling. So I'll go ahead and start those captures. So we'll capture 1/1 and click OK. We should see some OSPF hello messages and other stuff that's going on. Great, great, great. It's working. All right, let me go ahead and make that a little bit smaller for the moment. And let's also capture on E1/2. So we'll go ahead and right click again, click on capture. We'll specify E1/2 and we'll click on OK. All right, I'll make that also a little bit smaller and move it over here a little bit to the right just to make sure there's some activity on it. Good, good, good. So we can bring up the PC or the server. Let's go ahead and bring up the server. All right, so this represents the server. We'll just double check its IP address real quick by bringing up a command line. And let's do ifconfig for Ethernet 0. And sure enough, 10.9.0.106. This is hanging off of switch 6. So if we are going to do a ping over to, let's go ahead and ping server 3 on the left. And he is at 10.9.0.103 and press enter. I'm always a little shocked when it works so well the first time. Let's do a control C there. So what's happening behind the scenes is that this switch right here, switch 6, is taking those requests, wrapping them up, shipping them over the tunnel, and then switch 3 is de-encapsulating them, forwarding them down, and then for the replies back, the reverse process happens. Also, while the captures are still running, let's do a couple more things. Let's go ahead and do an SSH session. Let's do an SSH over to 10.9.0.103 and press enter. Okay, it's asking me if I want to trust the fingerprint. I'll say yes. And what is the password over there? Is it this? Let's see here. Is it that? Nope. Is it that? Nope. Okay. Really doesn't matter too much. I just want to make sure we can capture some traffic going back and forth between this server here on the right and this server over here in the same VXLAN, but yet in a separate part of the network. So let's go ahead and stop our captures and we'll take a look. All right. We could probably grab either one and get some traffic. Let's go ahead and start with E1/2, that interface, and take a look. And let me make the font a little bit bigger. So let's start with a ping, and let's go ahead and do a filter, display filter, looking for just ICMP traffic. And here we go, right here. So here we have traffic from 10.9.0.106. That was the server on the right, pinging 10.9.0.103. That's the server on the left. But check it out, because we captured the traffic as it was going over the logical tunnel. Look what it did. So let's take a look at what happened here. So the Ethernet frame is being sent, and this would be coming from the MAC address associated with the Ethernet 1/2 interface on switch 6, going to the layer 2 address of the next hop router. So that's the outmost Ethernet header. And inside of the Ethernet header is saying the next protocol is hexadecimal 800, which is IPv4. So here in the IPv4 header, the source is the tunnel endpoint address for switch 6, and the destination is the tunnel endpoint address for switch 3. And then in the header, it says, hey, the next protocol is UDP. And so here's the UDP header that was being used for the re-encapsulation of this tunnel traffic. And then after the UDP header, then we have a VXLAN header right here. And here it's identifying the VXLAN network identifier, the 6783. And that way when the receiving switch sees it, it says, oh, okay, great. It can de-encapsulate it and then forward it appropriately to the devices in the VLANs associated with that VXLAN. So once switch 3 receives this, it's going to strip off all of this information, and what it's going to forward is the original layer 2 header with the source MAC address of server 6 on the right-hand side and the destination MAC address of server 3 on the left-hand side. And then in this Ethernet header, it then points to the next protocol being IPv4, and then the payload for this packet was an ICMP echo request, which is right here. So from the server's perspective, they don't know that all this encapsulation and de-encapsulation happened. All they think is that, hey, we're two devices on the same subnet, on the 10.90 subnet. And it feels like, to these devices, it feels like we're right next to each other. So here's saying the response wasn't found, but it's very possible that the response could have come back on the other path. Because there's two layer 3 paths provided by the spine, so the response could have come back over the other interface. All right, so let's go take a look at SSH. We also did an SSH session, or we started one. Let's go ahead and do a display filter for that. And I'm going to go ahead and right-click and go to follow and say, let's follow the TCP stream. And that's going to close that and give us just a filter for that session. So if we pick one of these as being initiated by the server at 106, let's go ahead and grab this one right here. Everything in these first 1, 2, 3, 4, 5 entries here are based on the re-encapsulation and sending the traffic through the tunnel. So all this is for the benefit of the two endpoints of the tunnel, and then when the receiver gets it, switch 3, it would de-encapsulate it, and it would simply forward the layer 2 header, which from the MAC address, it looks like it's sourced from the MAC address associated with server 6, going to the MAC address associated with server 3. And then the next protocol is IP, and then at layer 4, it's TCP, and then we have the payload of the original request, which was an SSH message. So is it possible to have a TCP header and a UDP header? The answer is yes. Here we have UDP header that was part of the encapsulation and the tunnel traffic. And then after that got stripped off, the actual real protocol trying to be used by the client was using at layer 4 TCP in association with SSH. So let me go ahead and close those captures. And one last little test I'd like to do is just to validate that we're actually doing load balancing across the two interfaces as traffic goes from server 6 over to server 3. So here on leaf 6, if we do a show IP route to the other end of the tunnel, which is 10.10.10.3, we have two equal cost paths. And let's get a little bit creative and let's do a show interface Ethernet 1/1. And let's pick out a few elements that might be relevant here so we can filter them out with a pipe. And how about this? Let's go ahead and filter on the 30-second output rate right there. So I'm going to copy that to my buffer and let's do a show for that interface. We'll do a pipe and we'll put in some quotes, paste that in, and end quote and enter. And it says, Keith, you might want to put an include there. I thought it, doesn't that count? All right, sounds good. And then we'll do it again also for Ethernet 1/2. So to be a little creative, let's do this. Let's do a show interface Ethernet 1/2, looking for just the output that includes that line. Press enter, and we'll also do it for 1/1. And that way we can go back and forth. We can actually see the amount of traffic over the last 30 seconds that's currently being used. So currently it's about 80 bits per second, not very taxing. So if we bring up our server, and let's do this. Let's do a ping, and we'll say the size is 1,000 bytes. And we'll ping the target at 10.9.0.103. That should put some load, and there'll just be a continuous ping. And that way we can look at the output here and see approximately if it's doing a load balancing. So I'll go ahead and just let that run in the background, and let's go ahead and give that a moment. And let's look at Ethernet 1/1, and now it's at 2,000 bits per second, and 1/2 is about 1168. So we'll go ahead and give it a few more moments, and then we'll test it again. So both are being used. It's not exactly perfect, but if we had more clients, it's very likely to be more equally spread out. There we go. That's 3,100 and 3,300. Amazing. And we'll go ahead and do it again. And now it's 47 and 35. There's 5,200 and 5,500. So I also want to verify just by stopping my ping. I'm going to do a Control-C to stop the traffic. And then we'll give it about 15, 20 seconds. And then we'll look at it again. And those numbers should be dropping. So it's been about 30 seconds. And so I'm going to go ahead and look at both of them again. So we have 480 bits now per second on 1/1. And on 1/2, we have about 96. So let's go ahead and just verify that real quick. So there we go. They're both coming down. So let's recap. We have up here, we have switches that are at the spine layer. And there's full connectivity between each switch at the spine layer and each device at the leaf layer right here. Also, there's no cross connects. So we don't have cross connections between a switch 1 and switch 2 at the spine layer. No. We also don't have cross connects here horizontally between any of the leaf switches. Everything's going through the spine. We also took a look at the concept of tunneling and using VXLANs, which give us the ability to take any devices we want to pretty much anywhere here in the data center and logically place them on the same subnet. And that's done by tunneling the traffic between the switches. So the actual packets are being routed over the spine, but the logical tunnel is going from one switch over to the other switch. So when considering network designs and network topologies in light of the Cisco CCNA, I'd like you to remember two major families. One is the hierarchical model, which is the 3-layer model. We had a separate video just on that, and that's with the access layer, distribution layer, and the core. Or if you want to smash the distribution and core together as a collapse core, that'd be the 2-tier hierarchical model. And that's really great for like a campus network. If we, however, have a data center that we need devices to be able to communicate very quickly back and forth, even if they're on different hosts, we'd very likely be using a spine leaf model, as we've just discussed in this video. And if you want to, on top of that, leveraging VXLANs as well. So thanks for joining me in this video, and I'll see you, my friend, in the next live event or next video. Until then, be happy and treat everybody well. I'll see you next time.
What you putting in?